Hello student, now let's discuss one more problem of dynamic programming, that is longest common subsequence. So we will solve this problem with the help of dynamic programming. So first of all, let's discuss what is this. A longest common subsequence is generally used when we are given two sequences and we have to find out which subsequence is common as well as the longest. The real-time example of this longest common subsequence is comparison of two DNA string. Although we already know that the DNA of two human beings are different. That means every human being have a unique DNA strings. But to establish a relationship, a close relationship between two human beings, we have to find out DNA common subsequence, and if the length of the common subsequence between two DNA crosses the threshold value, then we can establish that those two human beings are related to each other. That means there is a biological relationship between them. Okay, so let's understand what is this problem. So let's say we have two sequences X and Y, and in this X and Y we have to find out the longest common sequence, and the longest common subsequence is BCBA. Okay, BCBA. There is a constraint that in this sequence, longest common sequence, the relative order of the alphabet or character should be maintained. Now, if we do brute force analysis of finding out the longest common subsequence, that would be very difficult and very time consuming, because if the length of sequence M is M and length of sequence of Y is N, then there are 2's power M total subsequences of X. And in order to find out these subsequences in Y sequence, we have to n comparison. So total number of comparison would be into 2's power M. This is very time consuming. So here we will to apply dynamic programming so that we can find out the solutions. So let's discuss why it is optimization problem. As we already know, there are a lot of subsequences may be possible which are common in both given sequences, but we have to find out which has the maximum length. So that's why this is an optimization problem. Here criteria of optimization is the length of the subsequence. Okay, now for application of dynamic programming, we have to follow steps of the dynamic programming. As per the first step of the dynamic programming, we have to characterize the solution. So our solution is find out the longest common subsequence. So here we characterize the longest common subsequence. For that purpose, let's consider assumptions. For a given sequence X, which contains m number of characters, we define the ith prefix of X, and value for I, it goes from 0 to m, is xi is equal to ith prefix of X is equal to x1, x2, xi. That means the first character of X becomes the prefix of X. For example, if X is equal to a, b, c, b, d, a, b, then x4 would be a, b, c, b, and x0 would be the empty string, or we can say epsilon. Okay, now there is one more important theorem that is very useful while finding out the optimal structure. That theorem is 15-point form in Corman, and as per this theorem, it says let x is equal to x1 to xm. That means x contains m character and y contains n characters, and the sequence z, which is common to these two sequences, contains the k characters, and let's say it is LCS. So three possibilities are there. If xm is equal to yn, that means last character of both given sequences are equal. That in that case, that symbol would be definitely part of the longest LCS, longest common subsequence. That means ZK would be XM equal to YN. That means ZK minus 1 is calculated on XM minus 1 and YN minus 1. Okay, this is the first case. Now come to the second case. If XM is not equal to YN, that means last character of the given sequences are not equal, and we are also sure Z K is not XM, that means last character of the LCS is not equal to the last character of the sequence X. That means LCS would be now calculated on XM minus 1 and YN. That means by considering M minus 1 character of X and N characters of Y. Similarly, if XM is not equal to YN, that is last character of the given sequences are not equal, and ZK is not equal to YN, that means last character of LCS is not equal to the last character of Y sequence. It implies that Z is an LCS of X and Y. This time we will consider M characters of X and N minus 1 characters of Y. Okay. Now, this theorem is very useful while writing the recursive solutions. So, now come to the step 2. In step 2, let's do one more assumption. Let Cij denotes the length of the LCS of sequence Xi and Yj. Xi is the prefix of sequence X up to length I. Yj is the prefix of Y up to length Z. If either I is equal to 0 or J is equal to 0, that means if any one of these prefixes are empty, then one of the sequence, then length of the LCS would be 0 because nothing would be common. Okay, the optimal substructural LCS problem can be written like this: Cij is equal to 0 if I is equal to 0 or J is equal to 0, that is if any sequence is length of the any sequence is 0. Cij would be Ci minus 1 J minus 1 plus 1, that means a length of the LCS for given sequences I and J of length I and J would be Ci minus 1 J minus 1 plus 1 if last character of given sequences are equal. Okay, the last character of Xi is equal to Y. Okay, now otherwise it would be Cij minus 1 or Ci minus 1 J, depending on which have the maximum value, and this would happen if Xi is not equal to Yj. If Xi is not equal to Yj, that means last character of given sequences are not equal. Okay, now let's discuss step 3 of our dynamic programming on LCS. As you can see, there is an algorithm in front of you. Now discuss. Name of this algorithm is LCS length, and it will accept two arguments, and those arguments of array type X and Y. That means array X of sequence X and array Y of sequence Y. Okay, and then length of X, let's say length of X is M and length of Y is N, and this for loop for I is equal to 1 to M, Ci 0 is equal to 0, that denotes that if the length of subsequence Y is 0, that means nothing would be common, and for every value of I, that means it doesn't matter what is the size of the sequence X, LCS, length of the LCS would be 0. Okay, so it signifies that these values are 0. Okay, for j is equal to 0 to n, C0j equal to 0, it signifies that if the length of sequence X is 0, it doesn't matter what is the length of Y sequence, nothing would be common and would remain 0. That means this denotes this situation. Okay, now after that come to the loop number 3 at line number 7 for I is equal to 1 to m, and there is inside this there is one more loop for j is equal to 1 to m. That means for every value of I, j would run n times. That means we have to fill our values row wise. That means in this table we will fill values row wise. Okay, now if xi is equal to yj, in that case, that means ith character of x is equal to yth character of j, then the value of the Cij would be Ci minus 1 j minus 1 plus 1, and there is one more table B in which you have to fill this diagonal arrow at corresponding index of the table. If this condition doesn't hold, that means xi is not equal to yj. There may be two possible. We have to find out two values, Ci minus 1 j and Ci j minus 1, and you have to do a comparison, and based on the comparison you decide two things. If this condition holds, then value of the Cij would be Ci minus 1 j, and then you will use this upward direction arrow. Otherwise, if Cij is equal to Cij minus 1, then you have to use this horizontal array. Okay, now let's do this analysis in our example. Okay, so in these two situation holds when value of the y sequence 0, and this condition holds when the length of the sequence x is 0. Again, for C11 we have to compare two things, this one and this one. Okay, if both are equal, then you have to use upper one, as the algorithm says, like this. Okay, and the upward arrow, then upward arrow. Okay, then C12. Now come to value C12 again. C12, we have to compare characters. If the characters A and this D are not equal, that means we have to jump into the else case. If they are not equal, we have to jump to this else case, and again we have to compare these two values, this value and this value. If both are equal, then we will use upper one and then appropriate array. Okay, again compare this C with this A. Again this is not equal, then we have to use these two values, this value and this value, and do a comparison. If both are equal, then we will use the upper one and then appropriate arrow. Okay, now we have to compare this A and this A. This time there is a match. If there is a match, what we will do? We will do a diagonal value plus 1. If there is a match, xi is equal to yj, then value of Cij is equal to Ci minus 1 j minus 1 plus 1, and then diagonal arrow. Okay, so in this case, this A matches with this A, and that we take the diagonal value. Diagonal value is the C. We are talking about of C14. The diagonal value will be C03. That means this value plus 1, then 0 plus 1 1, and the diagonal arrow. Okay. Again, now compare this B with this A. Both are not equal. Then we have what we have to do. We have to compare two values, this value and this value. This time, this left value is greater, so we will use here, and then appropriate arrow. Okay. Now again compare this with A. This with this A. Both are equal. That means we have to use diagonal value plus 1. So diagonal value is 0 plus 0 plus 1 1, and appropriate arrow, that diagonal arrow. Okay. Now let's do one more time, one more row. Okay, so now this we will compare this value with this value B. Both are equal. That means we'll use diagonal value plus 1. So 0 plus 1 1, and then appropriate diagonal. Okay, now compare with D with this B. Both are not equal. Okay, if both are not equal, that means we have to compare these two value. Okay, and if these two value we are going to compare, the which one is greater one, that means origin, that means value will come from here and appropriate arrow. Okay, now compare C and B, both are not equal, compare these two values 0 and 1, and 1 is greater than 0, so that's why we are using 1 and appropriate arrow. Now this time compare with this A and this B. A both are not equal, then we have to do comparison, this value and this value both are equal. If it is equal, then we have to use upper one, so we have to write 1 and appropriate arrow. Okay, now B and B, this time there is a match. If there is a match, we have to use diagonal value, this value 1 plus 1, then 2, then appropriate arrow. Okay, B and A both are not equal, that means we have to do compare 2 and 1, 2 is greater than 1, so we have to write 2 and then appropriate arrow. Similarly, you have to fill this table. In the end, the last entry of the table would be m into n. Okay, and in this case, it is it is 4, and this 4 signifies that what is the length of LCS. So the length of the common subsequence is 4. So come to the step number 4, which is the construction of LCS. That means what is the value of that particular LCS you have calculated. So that means it tells us about which characters are being used for the LCS. Okay, so it starts from this end. It takes the table B and X is the sequence X, and I and J denotes the index. This. Okay, so this is length of X and that is length of Y. The length of X is 7 and length of X is 6. So it is length of Y is 6. So it is 7 6. So it start from this end. And after starting from this, if any value I or j becomes 0, then it would return. Otherwise, there is a recursive call, and it totally depends on the direction of the arrow. That means which arrow here being used, and but after following that particular arrow, you call the new one. Okay. So for the initial call, it is bx76 and the first call, if bij, this arrow bij, this is not this arrow, this because this is a vertical arrow, but this is diagonal. So else if bij is this vertical arrow, then we have to call print LCS bxi minus 1j, that means 6 6. So this is 6 6, that means you are following the direction of the arrow. Initial call was this, and then now you have to call this, and again when you call this function call itself and again match. If bij is the directional array, then it would next call be bxi minus 1 j minus 1 bi minus 1 bxi minus 1 j minus 1. What is the value? 6 7 6. So it would be 6 5. So that would be a 6 5 this, and print xi, that means this particular character would be included in the LCS, as you have circled or here. It's already highlighted in this example, that means this is the part of the LCS. So again you have to call this now, and this time call would be bx and 5 5 bx5 okay. Now for the bx5, when you call this bx5, this time this condition hold, and then next call would be bx45 this is bx45. Okay, now this times you get the diagonal array and diagonal array, then you call the bxi minus 1 jn minus 1, that means b34, next time b34, and the print this value. So that means all values on which we get this diagonal array would be the part of the LCS, and you move by following the direction of this array until unless one of I or j becomes 0, and you are accessing that entries of this table, and the size of this table is n into n, m into n. So the complexity would be, and this algorithm is order of m into n. Okay, and the characters which are highlighted over here are those which came on the diagonal, like this, and this. These are the part of the LCS. Okay, thank you. Now we have already discussed the complexity. The complexity of LCS is order of m into n. Thank you.